Hello friends, in this video I have explained a simple VFD circuit or a variable frequency drive circuit. So what exactly is a VFD? Motors and similar devices don't really work well when they have to run at frequencies that aren't what they were designed for. If they do, they can become really inefficient and might even get damaged over time. For instance, a motor that is meant to run at 60 Hz shouldn't be used at 50 Hz or other frequencies. If you do that, it can lead to problems like the motor overheating, running too fast or too slow, and using way more energy than it should. This can make everything less efficient and shorten the life of the motor. Sometimes, though, you have to run motors at different frequencies, and that's where a VFD, or variable frequency drive, comes in handy. A VFD is a tool that lets you change the speed of an AC motor by adjusting the frequency and voltage of the power it gets, based on what the motor needs. This means you can use any AC motor with any power supply, no matter the voltage or frequency, by setting the VFD to match the motor's requirements. You usually do this by using a control knob that has different frequency settings on it. Okay, so now that you know the actual purpose of a VFD circuit, let's understand our own VFD circuit diagram. Circuit description. Referring to the full circuit diagram shown on your screens, this VFD, or the variable frequency drive controller circuit, is exclusively designed by me, and the main objective of this VFD circuit is to provide a sine wave output with adjustable frequency and RMS voltage for controlling the speed of an AC motor as per the standard VFD specifications. Here's how each section works. The inverter section. In this stage, the IC IRS2453 is configured as an H-bridge, full bridge inverter. It generates a square wave output, where the frequency is determined by the external components RT resistor and CT capacitor. The motor is connected to the output of the H-bridge, and its speed can be controlled by varying the frequency of the inverter's output. RT is made adjustable using a potentiometer, enabling precise frequency tuning. The SPWM Generator section. To transform the square wave into a sine wave equivalent, an adjustable SPWM, or sinusoidal pulse width modulation signal, is generated and integrated into the H-bridge. The IC555, configured as an astable multivibrator. The IC555 generates a fast triangle wave which acts like the carrier wave. This carrier wave is fed to the non-inverting input of the comparator IC741. The IC741 op-amp comparator. The slow triangle wave, which works like the reference wave, is derived from the RT core junction of the IRS2453 IC. This ensures synchronization between the SPWM and the inverter's output frequency. The slow triangle wave is fed to the inverting input of the comparator. The comparator compares the carrier and reference waves, producing an SPWM signal at its output pin 6 of the IC741. The integration with inverter. The SPWM signal from the comparator is integrated with the low-side MOSFET gates of the H-bridge stage. This modulates the square wave output of the inverter into an SPWM equivalent sine wave. Now you might be wondering how this circuit becomes a variable frequency drive. Okay, so the frequency and the RMS control features does the trick here. The frequency of the inverter's output, and thus the motor, can be adjusted by varying the RT resistor. This changes the reference frequency of the SPWM signal. The RMS voltage of the sine wave output can be adjusted by varying the duty cycle of the SPWM carrier wave. This is done by tuning the duty cycle control of the IC555 stage. These adjustments allow precise control over both the frequency and voltage of the inverter's output, making the circuit a fully functional VFD for motor control. Now let us discuss the key features of the circuit. The synchronization. The reference signal for the SPWM generator is derived directly from the RT core junction of the inverter IC, ensuring perfect synchronization. The flexibility. Both frequency and RMS voltage can be adjusted independently, allowing wide control over motor speed and performance. The simple design. The use of standard ICs like the 555 timer, 741 op-amp, and IRS2453 simplifies the design and makes it cost-effective. So folks, this concludes the full circuit description of the proposed VFD, or the variable frequency drive circuit. I hope you like the circuit concept and the circuit design. If you have any questions related to this topic, please don't hesitate to drop them in the comments. Wishing you all the best. Thanks for watching, and take care.